So, hello everyone. My name is Anush Kumar and I am PMR of TA for this course, Coordination Chemistry. And I am here today to discuss the assignment 7 for this course, right? We will be discussing questions related to colors and optical spectra. That is week 7, right? So, as usual, I will show two problems to you and I will wait for 2 minutes to get your answers and thereafter I will explain, right? So, the first two problems of the week 7 is so many coordination complexes are colored due to first is evaporation of solvent from the complex lattice, second is formation of solvent coordinated complexes in solution, electronic transitions in metal and d orbitals, or all options are correct. And the second one, you have to find the microstates for this term symbol, that is 3p, right? So just try to solve, and after that I will explain in detail. If you know the answer, just to type in the chat box. Any guess? Yeah. So if anybody know the answer, please type. You know already that the color is due to the transitions, right? So if any color is there, if any compound is showing any color, so every time it will be undergoing any electronic transitions as you study in the UV visual spectroscopy, right? So you can get an elementary idea from the basic principle of spectrophotometry, right? So electronic transitions is related to the color, okay? And the second one, you have to find the total number of microstates. So basically, the formula for calculating microstates is 2s plus 1 and 2l plus 1, right? So it is the value of spin multiplicity, that is 3, okay? And for this p, what you have to do, just write like this, okay? So you will be getting the value of l equal to 1. So that will be 3 multiplied by 3 equal to 9 microstates will be there. So here is the explanation. So the transition metal complexes often have spectacular colors due to electronic transitions in d orbitals by the absorption of light. So in the dd transition, an electron in a d orbital on the metal is excited by a photon to another d orbital of higher energy. If I talk about the case of octahedral complexes, so both are the d orbitals, right? And if any electron is here, right, and the energy is irradiated, this electron can transit to the higher energy states, right? So correspondingly you can calculate the wavelength at which the molecule uh, absorb the this light, right? But it will show the complementary color as discussed in the classes, right? So the next two problems, for a transition metal complex, if metal center is highly reducing and ligand is highly oxidizing in nature, then type of charge transfer occurs. You have to choose between ligand to metal charge transfer, metal to metal, you can say intermetal charge transfer, or metal to ligand charge transfer, or none of them. And the next question is due to the is asking about the dark red color of ruby crystals, right? As you study the doping of chromium oxide and alumina, right? You have to select the right option. So these questions are directly related to your theory part. If you know the answer, please just try to be involved in the solutions. So first is A, second in A. Okay, now I'm getting the answer. So metal center is highly reducing, right? If it is a reducing agent, what does that mean? It just donating the electron and reducing the ligand, right? If ligand is highly oxidizing, what does that mean? The ligand is donating the electrons. Sorry, accepting the electrons. That is reducing itself and oxidizing the metal. So from the basic definition, you can get the idea that if it is donating the electron, metal is donating the electron and ligand is accepting, so what it will be? It should be metal to ligand charge transfer. Clear? Here is just reverse. Yeah, it is metal to ligand. Okay, so here is the explanation. I have already explained, for a metal to ligand charge transfer transition, an electron may jump from a predominantly metal orbital to a predominantly ligand orbital, right? So these can mostly occur when the metal is in low oxidation state, right? That means electron is rich in rich in electrons, and it can easily donate, right? The second one is ruby is alumina containing a 0.21 atom percent of chromium plus 3, right, in place of the aluminum plus 3 ions. And in the, as discussed earlier, it contains some octahedral holes. Okay, so in ruby, the color is caused by the excitation of electron on a single dopant d metal ion, right? So it is a dopant molecule where the excitation of chromium 3d electron occurs, that is DD transition. Okay, so you can choose the answer accordingly. Yeah, the first one. So moving to the next two, the intense purple color of potassium permanganate is observed due to it is metal to ligand charge transfer transition, or metal to metal, ligand to metal, or ligand to ligand. Okay, and the next one, both the spin allowed and Laporte allowed DT transition will occur in case of. Here are two complexes. You have to just identify the transition will be spin allowed and Laporte allowed, right? So first one is octahedral complex and second one is tetrahedral. So basically in the B part or in B option, you are not getting any center of inversion, right? So from that you can get the elementary idea to solve this question, right? It is D8 and it is a high spin complex. So if I fill the electron, that is, so spin will be 0 in this case. And if I just write it like this, okay, so it will be 0, right? So a spin multiplicity may be same, right? So it can be spin allowed, but these orbitals are dd, both are d orbitals, right? So but they will not be Liporte allowed because this is not allowed, and these transitions are only allowed according to Liporte selection rules. So what will be the case, because here it is also having a D8 configuration, but there is no center of symmetry. And if I write the configuration in case of, because it is a tetrahedral molecule, it will be E and it will be T2. There will be not G because the center of symmetry will not be there. Okay, and if I fill the electron like this, so spin 0, and here can also be 0 if they are having a opposite spin quantum number, right? So here in this case it can be spin allowed, right? But what about the Laporte one? It will be Laporte allowed or not? In tetrahedral complexes there is some DP mixing. Okay, so DP mixing means it is T2, and if it is having a p orbitals, right? So there will be not any difference between this and this because both are triply degenerate. So these T2 orbitals will have some character of p. So that's why the Laporte selection rule is relaxed. And if there is a character of some unzeroed orbital, so unzeroed to zeroed can be allowed. So that is the case of Laporte relaxation rule, right? So this will be the right answer because it can show both spin and Laporte allowed DD transitions. And what about this one? Potassium permanganate, because it is having MnO4 minus, right? So manganese in +7 oxidation state. It is highly electron deficient. Okay, higher oxidation state means there is a favorable chance of ligand to metal charge transfer because ligand is already having electrons or lone pairs, can easily donate. So that transitions will impart the specific color, right? So here is the explanation. In potassium permanganate, magnesium in higher oxidation state and it show intense purple color, right? So involving charge transfer from molecular orbital derived from filled oxygen p orbitals to empty molecular orbitals derived from manganese 7. Okay, so if you see the manganese plus 7 electronic configuration, what it will be? It will be 3d0. That means it is having a vacant d orbitals. So the p orbitals of ligand can be can donate their electrons and overlap with the d orbitals of metal, right? If I talk about the second one, both the complex is high spin system, right? So one is electronic configuration is this, other one is this, right? So hence the spin allowed transition is possible without altering the spin state of electrons. But Laporte's transition is forbidden in octahedral complex. On the other hand, in tetrahedral complex, Laporte transitions is allowed due to some DP mixing. Right? So the next one, the color of transition metal coordination complex that absorbs in the 410 nanometer wavelength region will be. So basically, you have to think what color correspond to this wavelength, and the compound will show just its complementary color, right? So you can remember just like this. Okay. So if it is having absorption in the red color range, it will show the green color, right? Similarly, you can think about the others color. And the second one, the compound that absorb light of shortest wavelength. So here are metal is same, only ligands are changing. So on the basis of spectrochemical series, you have to think which ligand is strong and which is weak. If it is a strong ligand, it will induce a large energy gap between the orbitals, and E is reversely proportional to lambda. So large gap will be there. The shortest wavelength it will be absorbing. Okay. So just try to solve, please. Anybody? Second D. Okay. And what about the first one? So if I write the spectrochemical series I BR, I am skipping some ligand, right? It will be like this. So among these ligands, this fluoride ion is a very strong ligand. It will be uh, creating a large energy gap between the orbitals that will be showing the shortest wavelength. So D option will be the right one. And if I talk about the first one, if a complex absorbs in the 410 nanometer wavelength region, then the complex will be yellow colored. Okay, because corresponding color of 410 nanometer is violet. It will lie in this range, the first one. So it will be showing the greenish yellow color, right? You can just remember this table. Okay, from that you can get the elementary idea. And what about this one? I have explained. You have to just uh, keep these ligands in order according to the spectrochemical series, and you will be getting the answer. So the highest will be for the this one. So greenish yellow, that is option B, is the right one. Okay. So although DD transition is laboratory forbidden, it is giving color in solution because it is a high energy transition, it is a low energy transition, it is spin allowed in some cases, or you can say vibronic coupling. Okay. So the light pink color of this complex and the deep blue color of this complex is due to. Okay. If you are getting any clue, just tell me. Cobalt is in plus 2 oxidation state for both the complexes. Both are pi donor ligand. In octahedral complexes, the Lipote selection rule is somewhat relaxed due to this vibronic coupling, right? Because due to vibronic coupling, the symmetry of the complex is disturbed, right? So this one will be the right one. And what about the second one? Think about it. Yeah, vibronic coupling. Yeah, vibronic coupling is correct. And what about the second one? Any guess? Any guess? So basically, the color of both these complexes are due to DD transitions, right? Okay. And why it cannot be a ligand to metal charge transfer? Because cobalt is in very low oxidation state. That's fine. And why? It cannot be metal to ligand charge transfer because these ligands are already pi donor, right? So the transitions that will happen and that will impart the color is DD transitions. Okay, moving to the next, the compound that shows metal to ligand charge transfer is potassium dichromate, nickel tetracarbonyl, and this mercury oxide and nickel tetra aqua complex. And what about this one? The increasing order of wavelength. Okay, so just write the spectrochemical series and you will be getting the answer. I'm writing it for you, right? So first will be chloride one, then uh, this water and ammonia, and then cyanide. Okay, I hope you are getting the answer accordingly. Just tell me which option will be more appropriate. Second is C. Okay, the fourth one is the least. I think cyanide is the strong ligand, so it will be higher energy that will be showing the lower wavelength, right? And then first, then third, and then second. So C option will be right one. Okay, and what about the first one? Okay, so here you can see this is in uh, minus 14 plus 2 plus 6 oxidation state, so there is more favorable chance of LMCT. Okay, and among these three you have to identify which ligand is sigma donor and pi acceptor, right? So this oxygen is also a pi donor. Here is also oxygen. It is also pi donor. But in this case, nickel is connected through carbon. Okay. So the bonding here, it is sigma donor and it is pi acceptor, right? So in sigma bond formation, basically this carbonyl is donating its sigma electron to metal. But in pi bond formation, this nickel is donating its electron to this carbonyl because it is having electron rich configuration, right? Okay, so this option will be the right one because it will be showing the metal to ligand charge transfer. Okay, and apart from that, sorry, it is not having a D8 because here is in zero oxidation state. It will be having D10. Okay, So the next, you have to choose the incorrect statement, and yeah, the second one is also related to the spectrochemical series. If you know the answer, please tell me. First is A. Complex with a strong field ligand absorbs high wavelength light. Okay, right. That will be having a low wavelength. Good. The first one is incorrect. What about the second one? Just arrange them in their order, and first you have to see the energy order, and after that arrange them in order of wavelength. So the strong ligand will be showing the shortest wavelength. So here in this case, I think ammonia is the strongest ligand that will be imparting higher energy gap and corresponding low wavelength, right? So this option will be correct. Understanding my point? These are some basic questions, but little bit tricky. Okay. So what about this one? The last two questions of this session. The number of microstates in term this, I have already indicated the formula 2s plus 1, 2l plus 1. Okay, you have to calculate the value of L, just put into the formula, multiply, you will be getting the number of microstates. And in the second one, there is some isoelectronic series you have been given. Okay, so all members have intense charge transfer transitions. You have to choose the incorrect statement among these. Okay, just calculate. I think I'm getting the answer now. So first C. Okay, 9. So let me calculate also. It is L will be, sorry, so 2s plus 1 and 2l plus 1. That will be 1 into 2, 4, 8, 9. Yeah. What about the second one? You know the color of permanganate. It is highly intense. Okay, if I talk about the charge on the metal nucleus, here what it will be, it will be, I think, plus 5, right? Here it will be plus 6, and here it will be plus 7. So the charge order is correct. Okay, the wavelength of transitions increase in the order because the oxidation state is increasing. There is a higher chance of ligand to metal charge transfer, and there will be higher intense charge transfer transitions. So the wavelength of transitions will also increase in this order, and transfer transitions are attributed to excitation of electron from ligand to metal. Yeah, this is also correct. And what about this one? This permanganate ion exhibit charge transfer at shortest wavelength among the three. No, it is having a highest wavelength. Okay, so this will be the incorrect statement. Okay, so it was all about today's session. If you have any query, please tell me. Okay, otherwise, I will close the meeting. Yeah, very thank you, Dr. Vidyalakshmi, for attending this session. Any question? Okay, so thank you very much for attending. Yeah, I'm closing now the meeting. Bye bye.